Now we're going to look at the quadratic formula method for solving trig equations. First, let's consider how we use the quadratic formula when we talk about algebra. In algebra, we have something like x squared, usually we put an a in front of the x squared, plus bx plus c equals 0. So typically when we solve using the quadratic formula in algebra, we'll have something in what we call quadratic form, and usually we call this standard form. We have the quadratic term first, or the thing that's being squared, that term comes first. The second one is what we call the linear term, the bx with x to the power of 1. And then the last term that doesn't have an x in it, we usually call that the constant term. We always have to put everything on one side and equal 0 on the other side before we begin using the quadratic formula. The quadratic formula itself is always x is equal to, so we always have the x by itself on one side equals negative b plus or minus square root b squared minus 4 times a times c, all of that divided by 2 times a. Now the difference is when we're talking about trigonometry that we usually don't have an x in the problem. Instead of x and x squared, we might have something like cosine squared x and cosine. Or we might have sine squared and sine. So when we actually go to solve using the quadratic formula for a trig equation, instead of having x that we're solving for, we actually end up solving for either something like cosine or sine, one of the trig functions. So we get the trig function by itself on one side. That's how we isolate the trig function. Equals, and then all of the a's and b's and c's are the numbers in front of those terms. The other really important part about using the quadratic formula is this is not your answer. What you get on the other side of the equal sign is the ratio. So you don't want to stop there. When you're in algebra, you stop there, but when you're in trig, this is your ratio. So the next step after you get to this stage is to take that ratio and put it into the cosine inverse function. So you have to put the ratio inside. Or if you're dealing with sine, you'll be putting into the sine inverse function. If you're dealing with tangent, you put it into the tangent inverse function. So whatever trig function is used throughout that equation, you have to put the ratio into the inverse function first, and then on the other side you get your solution for your angle. Alright, so that's a basic overview of the method. How do we apply it to a particular problem? So let's look at number 5. Cosine squared theta minus cosine theta minus 1 equals 0. So first of all, if I were to think about this in terms of the algebra, we let the trig function be represented by an algebraic variable. Let's just say for this case w. So that would be w squared minus w minus 1 equals 0. So that's kind of the algebraic form of that. I could try to factor that, but using my factoring techniques, that won't factor. If something doesn't factor, then we go towards our quadratic formula. So our quadratic formula in this case would be to make sure, first of all, that everything is on one side, zero's on the other, and that the quadratic term, the term that's being squared, is listed first. So the order matters here. The linear term, we want to make sure that's listed second. And then the constant term, we'll make sure that's listed last. The reason why we say the order is important is just because you want to make sure that you know what your a and b and c are. So the a value would be what's in front of w squared there. The b value would be negative 1, what's in front of just the w, and then the c value is the constant. So our algebra then would be to solve for w. W is equal to negative b. I'm going to put parentheses right now everywhere I see a letter. So negative parentheses plus or minus square root. I'll have parentheses squared. That's my b squared minus 4 times a, put parentheses, times c, I'll put my parentheses, all of that divided by 2 times a, parentheses. Alright, so be really careful, the b value is -1, so it brings its own negative. So negative b plus or minus the square root of b squared, so I'm going to put a -1 there in place of b. -4 times a is 1. Our c value is -1, so be careful about your signs there. All over 2 times a is a +1. Alright, and there's everything put into our quadratic formula. Okay, you should know the quadratic formula, make sure that you know it. You should have that memorized, really. So make sure you're working on that. So we get w equals negative, that's a +1, plus or minus the square root. That's 1. -1 squared is a +1. Then I have -4 times a +1 times a -1, that's a +4. All of that divided by 2. So we end up with w is equal to 1 plus or minus the square root of 5 all over 2. Now what you want to be careful about again is that that is not your solution. You have to go back to the trig. It's always a push and pull between algebra and trig. What did we let w represent? Well, w is representing cosine theta. So we have to go back to cosine theta is equal to 1 plus or minus the square root of 5 over 2. Remember, really important, this is not the answer, this is the ratio that we would use to help us solve for theta. We're solving for theta, we're solving for that angle in between 0 and 2 pi, so just the standard one time around the unit circle. All of our solutions have to be positive and in radians. Now, we actually get two ratios, right? We have cosine theta is equal to 1 plus the square root of 5 divided by 2. And on the other hand, we have cosine theta is equal to 1 minus the square root of 5 divided by 2. So we actually do end up with two ratios because of that plus and minus. Now what I like to do, and I would encourage you to do the same thing, is to figure out what these ratios actually are. So I'm going to put it to my calculator, and I'm going to use Desmos here. 1 plus the square root of 5 divided by 2. Okay, so there's 1 plus square root of 5. I'm going to highlight all of that and put divided by. Make sure all of that's on top of the fraction, and I put 2. So I get about 1.61 and so on. I'm going to go back and put that into my notes. Okay. So what do we know about cosine? We should know by now that cosine ratios actually only bounce between -1 and 1. This ratio is actually too big. Alright, so let's see what happens. Let's say that I didn't know that. In order to figure out this angle, I would need to feed that ratio that we got. And I'm not going to round the ratio, but I'm just going to put ... for the moment and use what's in my calculator. But I need to put that ratio really into the cosine inverse function to figure out what the angle theta is going to be. So let's go back and do that in Desmos. So down here I'm going to go to functions, I'm going to do cosine inverse, and I'm going to type the same thing in. 1 plus square root of 5. I'm going to highlight the 1 plus square root of 5 with the mouse. I'm going to put divided by, make sure all that's on top of the line, put the 2 at the bottom. It tells me undefined, which essentially is telling me there's no solution. No solution. Alright. Now what about cosine theta is equal to 1 minus square root of 5 divided by 2? Let's figure out what that ratio is. Let's try and come up here and put a minus. So this is the ratio. Remember, that's really important. This is the ratio that I'm getting. This is not the answer, but this is what my ratio looks like. This is the exact value. This is the approximation of that ratio. So I'm going to go back and just put that into my notes. Try not to round that ratio. Now in order to figure out the answer, we have to put this ratio into the inverse trig function. A lot of times that's the biggest mistake. We just get that ratio and then we think we're done. But the ratio always has to be put into the inverse trig function. What we're looking for is not the ratio or even the approximation of the ratio. So this is the exact ratio, but this is just the approximate ratio. It's nice to know what that approximately is sometimes. I like to find it before I put it into the cosine inverse function, but you don't have to. But I like to kind of play around with that and see what it is first. What we get out of the cosine inverse function when we plug that ratio in, that is going to be our angle solution. Now we have to do what we always have done, right? We get the trig function by itself on one side. So that's step 1. Step 2, quadrant check. Okay, what quadrants are we looking in? Our cosine ratio is negative. So if I do all students take calculus, cosine is positive in quadrant 1 and 4, so I don't want those. We want to have a negative ratio. So we're looking in quadrant, quadrant 2 and quadrant 3. Couple of things then. We want to make sure that our angles come from quadrant 2 and quadrant 3, so we want both. And we also want to make sure that our answer is positive because it has to fit between 0 and 2 pi. That means positive radian measures from one time around the circle. Alright, so we need to know what our reference angle family is. Alright, so we want a quadrant 2 and a quadrant 3 solution. We got that. Alright, so what is our reference angle family? Let's go to our calculator. And I'm going to do cosine inverse, and I'm going to put that ratio into our calculator. Make sure that you are in radian mode, and we are, but just do a double check. Let's look at it, what look like in degrees. In degrees, that give me 128. If I see a really large number for my solution, for my angle, then I typically guess that it's not in radians. Alright, so radians are typically between 0 and 2 pi, or 0 and, what was that, 6.28? So this is in radians, and that's what I want. Alright, so I get about 2.2370 radians for that angle. We're going to round to the nearest 2 decimal places in a bit for our final answer. But right now, let's leave it as it is. Let's not round it. And let's work with trying to find out what quadrant is this in, and how do we find the other quadrant angle. Alright, so I have my quadrants, and I have my quadrantal angles labeled from 0 to pi over 2, pi, 3 pi over 2, and 2 pi, and I have the approximations written beside them. Here is the angle that our calculator gave us when we put in the ratio. Alright, so we want to figure out what quadrant that's in. That is going to fit between 1.57 and 3.14, so that is a quadrant 2 angle. Alright, so there's that angle. Just getting a good approximation of that. Alright, so what we want, remember, to find a quadrant 3 angle, we need the reference angle. So we still haven't found that reference angle yet that we need. What is that reference angle and how do we find it? Alright, so our reference angle then would be thinking about if I went all the way to here, that would be pi. That's too big. So we're going to do pi minus. We're going to take away, actually this part, right? Because we want the yellow part, we're going to take away the part in blue. Because this is what we want to find out, the yellow part. So that would be taking away that angle that we were given. Alright, go back and put that into our calculator. Alright, and when I do pi minus that, I get about 0.9045 and so on. So I'm going to copy that back to our notes. Alright, so there's our reference angle, the 0.904 and so on, and here I've written it here as well. So that's our reference angle. Remember, the whole point of that is to figure out what is our quadrant 3 angle. So the only thing we know about our quadrant 3 angle that we're looking for is that it has the same reference angle as the quadrant 2 angle. So I'm going to draw a quadrant 3 angle, and I'm going to copy and paste that yellow distance from the x-axis into quadrant 2, we're going to copy that as the distance from the x-axis into quadrant 3. Now remember, once we have kind of marked off that quadrant 3 angle, what we want to know is if we started at 0 and we rotated and we stopped here, what is that quadrant 3 angle with that amount of rotation? So that means I'm going to go the top half of the circle, which is pi, and then I need to go this yellow distance more, which is that reference angle. Alright, let's put that into our calculator and see what we get. Alright, so when I put that into my calculator, pi plus that reference angle, I get about 4.046 and so on. I'm going to copy that down to our notes. Alright, so here's the angle that our calculator gave us for pi plus that reference angle. Let's double check. Is it a quadrant 3 angle? For it to be a quadrant 3 angle, it has to be between 3.14 and 4.71 approximately, and it is. So it's definitely a quadrant 3 angle. So what are our two solutions? Our two solutions are the quadrant 2 angle. We're going to round to the nearest two decimal places here. So 2.24 from quadrant 2 and 4.0, rounding to the nearest two decimal places, that would round that up to a 5. So 4.05 for that quadrant 3 angle solution. Alright, so our final answer here in the solution set brackets would be 2.24 and 4.05. Alright, here's another example of using the quadratic formula to solve an equation. We are going to first look at the algebra here. We have two different trig functions. I have cosine x and I have sine x. And in algebra, they would both be represented by a different variable. So let's do z and w. So that would be like 3z squared in algebra plus w equals 2. If I was going to use the quadratic formula, I would think, well, let's bring everything over to one side, 0 on the other, so I would subtract 2 from both sides. But right away we have a problem because the quadratic formula doesn't work if the algebra has two different variables. So it's not going to work if I have a z and a w. It only works if I have one variable throughout the entire equation. It also is not going to factor because we have those two different variables. So we have an algebra problem, and if we have a problem in the algebra, then we go back to the trig and we look at a trig identity replacement. Alright, so this is going to bring us back to what we talked about in the last video. We can't do anything with sine. We can't replace anything for sine because sine isn't being squared. In order to use the Pythagorean identity, it would have to be squared. We can't use a double angle formula because our double angle identities have to have double the angle on the inside. So we're not going to be able to do anything for a replacement for sine, but we can do something with cosine squared. Because it's squared, that allows us to use a Pythagorean identity. Alright, I'm going to go back up to the very top of our notes and let's look at the identities that we have. Okay, so here's our Pythagorean identities. We have a Pythagorean identity that relates cosine squared and sine squared. So this is the one that we're going to use. Now one thing that I want to mention, so let's talk about this. The identity that we have on our page looks like this. Now keep in mind something, there's a big difference between theta and x used in the equation. So here's what I don't want to do. I don't want to replace cosine with 1 minus sine squared theta. Okay, the input angle that's used as the variable in the trig equation, I want to make sure that I keep that. So here's what I'm going to do before I even do any rewriting and replacement. I'm going to rewrite this as cosine squared x and sine squared x. So I'm going to use x as the variable throughout that Pythagorean identity. Now what do we want to do? We want to replace cosine squared x with something that it's equivalent to. So I need to get cosine squared x by itself on one side. So in order to do that, I'm going to subtract sine squared x from both sides. So I end up with cosine squared x is equal to, therefore replaceable by 1 minus sine squared x. So I'm going to put parentheses every time I do an identity replacement, and I'm going to write into that parentheses 1 minus sine squared x. Alright, so now throughout this entire equation we don't actually have z anymore, or cosine, we just have sine. So now we're in terms of all the same variable throughout the equation, and the algebra is going to work. Alright, so let's rewrite this and get it ready for using the quadratic formula. I'm going to distribute the 3 into the parentheses. So 3 times 1 is 3. 3 times negative sine squared is negative 3 sine squared x. And we have that plus sine x equals 2. Regardless of what method, factoring or quadratic formula, we always bring everything over to one side and 0 on the other. And we talked about that we like a particular order. So as I come down here, I'm going to write negative 3 sine squared x plus sine x, and then I'm going to subtract 2 from both sides, and that gives me the equal 0. On this side, when I combine like terms, negative or positive 3 minus 2, that's a positive 1. Alright, so one thing you could try to do at this stage is you could try to factor that. I'm going to go ahead and let you know that it wouldn't factor. So we're going to go ahead and apply the quadratic formula. Oftentimes when we use the quadratic formula, we prefer that the first number, the a value, be positive. You do not have to change it. You can solve the problem exactly as it is. But I'm going to go ahead and I'm just going to divide through everything on both sides by a negative 1. This is optional. Again, you do not have to do this. Your answer will be exactly the same if you don't. However, sometimes it just makes the problem a little bit nicer if that a value is positive. So that changes this to be a positive 3, and then changes the middle term actually to be negative, because a positive divided by negative is a negative. And then it changes that last constant there to also be a negative 1. And then 0 divided by anything is still 0. Okay, so that's optional. You don't have to do that. Your answer will be the same. Sometimes it just makes the calculations a little bit nicer. Alright, so are we done? No. Remember, we need to solve for sine x. We want sine x by itself on one side. So our quadratic formula would be sine x is equal to negative b plus or minus square root b squared minus 4ac all over 2a. So I like to put parentheses everywhere that I have an a, b, or c in my quadratic formula. And I'm just going to start plugging things in. Our b value is a minus 1. So it's like an implied minus 1 there in front of sine x. All right. And then our a value is 3. And then our c value is minus 1. Alright, so we have negative 1 plus or minus the square root of negative 1 squared minus 4 times 3 times negative 1 all over 2 times 3. Alright, we just want to simplify that ratio. This gives me a positive 1 plus or minus the square root of. I'm going to simplify all of that, and I get 13 all divided by a positive 6. I'm just going to bring this work up here. Alright, so we actually have two different ratios, right? We have sine x is equal to 1 plus the square root of 13, all of that divided by 6. And then we have sine x equals 1 minus the square root of 13, all of that divided by 6. So I'm just going to remind us that what we have is the ratio on the right hand side. This is not our final answer. This is the ratios for the angle we want to find. And remember that the angle we want to find is the x value, And the given interval for both of these equations was to solve between 0 and 2 pi. So positive angles only, radian measures only, and then one time around the unit circle only. Alright, so what I'd like to do is to put these into our calculator to figure out what the approximate value of those ratios are. So I'm going to go to Desmos and I'm going to type those in. So 1 plus the square root of 13 divided by 6 is about 0.767 and so on. I'm going to copy that back to our notes. Alright, so that's the approximate value of our ratio. We know that sign ratios are going to bounce between -1 and 1, so that's an allowed ratio. Alright, so our ultimate goal again was to get sine x by itself on one side. So the next thing that we're going to do here is do a quadrant check. Alright, since we said that was an allowed ratio, this will pop up in two quadrants. Let's do all students take calculus. The ratio that we're given here is a positive ratio, so we're looking at quadrant 1 and quadrant 2. Alright, then the third thing we always do is we find our reference angle family. That we don't know just by looking, so we're going to have to put that ratio into our inverse trig function. Alright, so let's put that into our calculator and see what we get. Alright, I'm going to use sine inverse, then I'm going to put in 1 plus the square root of 13. Highlight all of that, put divided by 6. So my calculator gives me an angle. Remember, this is the ratio. We're feeding the ratio to the inverse function, and it gives us the angle in radians. So our radian measure angle is 0.875 and so on. So I'm going to copy that back down to our notes. Alright, so here is the angle that our calculator gave us. That is 0.875, and we're going to look at our quadrants. We're looking for an angle in quadrant 1 and quadrant 2. And let's graph the angle that the calculator gave us. That will be in quadrant 1 because the angle is between 0 and 1.57. Alright, so it turns out that that is actually our reference angle because that is the distance from the x-axis to the terminal side of that angle. So that actually is our reference angle. Alright, so then that's actually also one of our solutions, right? We're going to round to the nearest two decimal places, so that's actually our quadrant 1 solution. That would be 0. If I round that to the nearest two decimal places, that gives me 0.88. Alright, so there's one of our solutions. We need our quadrant 2 solution, and the only thing we know about the quadrant 2 solution is that it'll be the same distance away from the x-axis into quadrant 2. So we're going to copy and paste that reference angle, or that yellow distance, into quadrant 2. Alright, how do we find that quadrant 2 angle? So we're going to think about if I start at 0 and I went all the way around to pi, that would be too much. We want to subtract off the part we don't want, which is the reference angle. Alright, and so to get our quadrant 2 angle, let's put this in our calculator and see what we get. Alright, so our calculator gives us about 2.2665 and so on, so we're going to copy that down to our notes. Alright, so there's our quadrant 2 angle solution. We want to keep two places after the decimal, so we'll look to the third, and that will actually round our solution up. So we get 2.27. Alright, so there's our quadrant 1 and quadrant 2 solution for that first ratio. The next thing we need to do is we need to look to what do we get from that second ratio, the 1 minus the square root of 13 divided by 6. Alright, so let's find the approximate value for that ratio in Desmos. Okay, so that would be 1 minus square root of 13 divided by 6, so we get this negative value, negative 0.434 and so on. I'm going to copy that into our notes. Alright, so there's our approximate ratio. We're going to do quadrant check. So our quadrant check, since we have a negative ratio, would be all students take calculus. It's positive in quadrant 1 and 2. We want to know where that ratio is negative for sign. So that would be quadrants 3 and 4 this time. Alright, so remember this is still the ratio. We're looking for what is the angle solution. In order to find our reference angle family, we need to feed that ratio to our sine inverse function. Alright, so we'll put that into our sine inverse function in our calculator and see what we get. Alright, so I have sine inverse of 1 minus the square root of 13, all of that divided by 6, and this is our angle measure. So remember, this is the ratio. When we feed that ratio to the sine inverse function, we actually get an angle measure in radians. Alright, so I'm going to copy this angle measure into our notes. Alright, so here's the angle in radians that my calculator gives me. So I'm going to graph that. Since it's a negative angle, that means I'm going to start at 0 and we're going to move in the clockwise direction. Alright, so there's that angle. Our reference angle is actually going to be the angle that's positive, the positive distance between 0, and the x-axis, and the terminal side of that angle. Alright, so our official reference angle will actually be the positive version of that angle. Alright, so there's our reference angle in blue. Alright, and what we have to be careful about is to remember again that our solution has to be positive, has to be a positive angle from quadrant 3 and quadrant 4. So I want to think about what would this angle be in quadrant 4, which is a place that I want to find an angle. I want to start though at 0 and then wrap all the way around and then stop at that quadrant 4 angle, getting to it from the positive direction, from a counterclockwise rotation. So how do I figure out what that amount of rotation is in the positive direction? So what would that be? That's going to be 2 pi, so thinking about going all the way around the circle, and then subtracting off that reference angle. Alright, so I'm going to put this into our calculator and then we'll see what we get from that. Alright, so my calculator, when I type in 2 times pi minus that reference angle, I get about 5.83 and so on. So I'm going to copy that back to our notes. Alright, so here's the angle that I got in my calculator. That is our quadrant 4 solution. So I'm going to put that on our line here above quadrant 4, and I'm going to round that to the nearest 2 decimal places, so that'd be 5.83. Now notice that we still need here our quadrant 3 solution. So we're going to copy and paste that reference angle into quadrant 3. Alright, so I put my reference angle from the nearest x-axis into quadrant 3. So now I want to be able to describe what is that quadrant 3 angle. So to find the quadrant 3 angle, I'm going to start at 0. I'm going to go all the way through quadrant 1 and quadrant 2, and then I have to go a little bit more. So right now I've gone a distance of pi, and I need to go this blue section more to stop there at the quadrant 3 angle. So the calculation for that would be pi plus that extra blue part that represents that reference angle. Alright, so let's put that into Desmos, into our calculator, and see what we get for that calculation. Alright, so in my calculator I have pi plus that reference angle, and I get about 3.59 and so on. So I'm going to copy that into our notes. Alright, so here's what I got from my calculator, and I'm going to round my final answer to the nearest 2 decimal places. So that gives me 3.59 for that quadrant 3 solution. Alright, so our final answer here is the 0.88, the 2.27, the 3.59, and the 5.83 that we got from all four of those quadrants.